Alright, so welcome back to the second part of the third week where we are talking about the longest increasing subsequence problem. So remember that here the input was an array of numbers. And what we were looking for in the output was the length of a longest increasing subsequence in A. So what we did was to propose the following idea where we said that we will write down a table which in its ith entry will store the longest increasing subsequence of the of the suffix array that starts from I and goes all the way till the end. And we know that our base case is sorted because we can say that dp of n is 1. We also know that the final answer that we are looking for lies in dp of n, because we also know that the final answer that we are looking for lies in dp of 1, because if you look at I being 1, that's essentially the entire array A, so that's just lis of A. So dp of 1 is going to give us the answer that we want. But where we got stuck was when we were trying to write the recurrence, we wanted to say something like dp of I is dp of I plus 1. But then we were not sure about whether we should add 1 or not, because that depends on whether the solution that we get for the subarray that starts at I plus 1 is extensible with the ith element or not. And in some sense, our dp table is missing this piece of information, or our recursive approach is not somehow being able to feed us this information when we need it. Right? So we are going to go back and try and enhance our dp table and basically give it a richer semantics so that everything actually works out. Okay, so remember what we are trying to understand is the nature of the starting point of the longest increasing subsequences in the subproblems. Yes, so we know that if you look at the space of all the increasing subsequences of the array ai plus 1 till n. So this is the subproblem from which we are trying to draw information, right? So we are going to have a bunch of these subsequences. And from our point of view, they fall into two categories. So these are ones which are not compatible with a of I, which is to say that if I took the element which was a of I and tried to prepend it to any of these sequences, they would cease to be increasing sequences. They would not be increasing anymore, which is basically the same as saying that these sequences start at numbers which are smaller than a of I. So I have the direction of the inequality wrong. So yeah, this would be a problem, right? So for example, if a of I is 9, but now you give me a sequence that is, I don't know, something like this, then this is not compatible. I cannot add 9 behind 3 and get away with it. This is not going to work. So some of these increasing subsequences are not going to be compatible with a of I, while the others would be, in the sense that these numbers are going to be even bigger than a of I. Okay, and if that's the case, then I can take the element that is at the ith index and add it behind these sequences, and these sequences would actually extend by 1. So the question of interest is, where are the longest subsequences, the longest increasing subsequences, if there's even one that is sitting somewhere here in the zone that is compatible with AI, that's when we do the +1. But if all the longest sequences that are increasing are sitting here, then we cannot do the +1. Okay, so that's the driving idea of the recurrence. And how should we capture this in the DP? Well, let me propose an extended DP table which brings in this extra information about where these subsequences start. Okay, so DP of I comma j now. So this is going to store the length of a longest increasing subsequence in the subarray that begins at j and ends at n. So in the subarray j to n, such that, well, now we want to capture the information about the magnitude of the elements in this increasing subsequence. So among all the subsequences, I'm only interested in those which are compatible with AI. This is what I'm looking for. So I want to say that the first element is larger than AI. This will ensure that whatever we have here, if we wanted to prepend it with AI, then we will be able to do that, right? But now, of course, we are now solving a different recurrence, so we have to figure out a recursive relationship for this DP. We cannot jump back to our old DP. We have to actually figure out how we can compute these DP values, right? Again, let's spend a moment talking about the base case. A natural choice for the base case would be when j is equal to n, because that's when you're looking at a singleton array. And we're thinking about DP of I comma n. What does this mean? We're just looking at a of n here. That's the last element in the array. And this is going to be a 1 or a 0 depending on what. Take a minute here to just figure out what this should be. So this is going to be a 1 if I is such that a of I is smaller than a of n, and it's going to be a 0 otherwise. So if a of I is at least a of n, then this value will be 0. Just to be sure that we're on the same page, let me work this out with an example. So again, let me put down a bunch of numbers here. Let's say that's our entire array, and so this is our last element. And let me write down the indices here. By the way, you may have noticed that I'm indexing my array starting from 1 as opposed to 0. If you're writing code, you may have to adjust for this because most programming languages will have their indices starting from 0. So let's say I want to figure out what is DP of 4 comma 10. Well, the answer to this is 1, because if I look at A of 4, that's 17, and 17 is compatible with 37. can you give me a dp value which is 0? For what x would this be true? So I hope you had a chance to think about that. Well, notice that dp of x comma 10 is 0 only if a of x is bigger than 37. And in this example, we have only one number for which that is true. So the only value of x for which dp of x comma 10 is 0 is going to be 7. So dp of 7 comma 10 will be 0. Everything else is going to be 1. Okay, so that's the story with the base case. Now, what about the answer? Previously, finding the answer was easy because we said that's just dp of 1. But now we have, well, we have dp of I comma 1, which will give us the length of the longest increasing subsequence in a of 1 to n. So that's the entire array, but only those whose starting points are bigger than a of I. So how is this useful, and how does it give us the length of the longest increasing subsequence for the entire array? Well, one thing that you could do is just take the max of these values over all I, because you know that the optimum answer is going to start somewhere. You don't know where, but wherever it starts, suppose it starts at 3, right? Then everything else in the array is going to be bigger than whatever the value is at a of 3, right? So just take the max of all of these and add 1 to it to account for the starting value, and that would be a valid answer. Another way to do it would be to take your input array and add a sort of dummy value at the beginning, which is a very small value. It's smaller than the minimum number in the array, right? So just symbolically, I'm going to denote that by minus infinity, although that's not an actual number that you can put in, but find the smallest value in the array, come up with something smaller than that, and add it to the beginning. And now just ask for the value of dp of 0, 1, right? So that's going to give you the length of the LIS in this array, where the starting point is at least minus infinity or is greater than minus infinity, and that's going to be pretty much the space of all the longest increasing subsequences. And notice that that's really not a constraint at all, so you're actually going to get your answer. So both of these methods of getting to the final answer are equally valid, and you can pick whatever you find convenient. Okay, all right, so we know how to get the final answer. We also know how to work out the base case. So now the only thing that remains to do is to actually work through the recurrence. So we have to figure out how to compute dp of I comma j. Once again, recall that we are working with the subarrays starting at the jth index, and we are looking for LIS where the starting value is bigger than whatever is at the ith index. Okay, so that's what we are looking for. So if you want to think about this for yourself and puzzle it out, this would be a good place to pause and ponder. But otherwise, we are going to dive right in and try to figure out what the recurrence should look like. So one place to start is to consider the case when a of I, the element at the ith index, is already at least the element that is at the jth index. So remember, we are dealing with this subarray here, and what we have already computed, hopefully by now, is dpij values for j plus 1 and so on up to n. Okay, so we must have done it for n because that was the base case, and remember, we're working our way backwards. So we want to progressively go further into the array to the right when we are thinking about what recursive information we can invoke, right? And I claim that if you are in this situation, then you have an easy way of moving forward. The reason for that is Notice that among the things you're looking for, which are longest increasing subsequences where the first element is larger than AI, we can say for sure that such a subsequence is not going to start at AJ because AJ is not bigger than AI, right? So we can immediately rule out the jth element from our consideration and just try to figure out what the answer was in the subarray starting at j plus 1. So that's in this situation, assuming that AI is at least A of j. So basically the jth element has no chance of participating in the kinds of solutions that we are looking for. So if this is the case, then what we are going to do is we are going to say just pull out the answer for j plus 1, right? So that's what's going to happen here. But on the other hand, maybe A of I is in fact smaller than A of G, right? So what if A of I is strictly smaller than A of J, or in other words, A of J is strictly larger? That means that the thing that we are looking for could potentially be starting at A of J, but it could only be potentially starting at A of J. There's no guarantee that the longest increasing subsequence that we are looking for must start at AJ. In fact, it's possible that if you insist on starting on AJ, you get stuck at AJ itself and you end up with something suboptimal. So interestingly, at this point, we don't know. We don't know if AJ is partaking in the thing that we are looking for or not. So we cannot throw it out, but we cannot also confidently add one and say move on. Okay. Now, when we are in this sort of a situation where we don't know, last time when this happened, we got completely stuck. But this time, because we're storing some extra information, what we can do is actually try both possibilities. And this is going to be the key to the recurrence here. I'm going to say, well, what if the jth element actually participated in the solution? Well, then I know that the jth element participated, so that gives me one element in my solution, and now I can move on to the rest of the subarray, which starts at j plus 1. But now, because I am assuming that I will be including the jth element, I will now look for only those subsequences which start at a value that is bigger than AJ. Right? So I hope that makes sense. That's because I'm assuming here that I do want to hold on to the jth element and include it in my answer. But what if the jth element does not participate in the optimal solution that I'm looking for? Well, in that case, just like before, we move on, because that's the same as the situation that we had earlier, where we could confidently say that J is not participating. Now it's just one of our possibilities. So we move on to J plus 1, but we maintain a threshold of I, because there's no reason to upgrade our threshold to J, because I'm assuming now that we are not including the jth element in our solution. So we have two options here, and both of these values will be given to us by the DP table. And what we need to do is just pick the better of these two values, right? So whatever is giving us more leverage, that is going to be our answer. Okay. And you can pause here for a second and, convince yourself that all this adds up. Okay. So really in one situation, we have an immediate reason to discard AJ. So we quickly move on to the subarray starting at J plus 1. In the other case, we don't have such a reason, but just because we can doesn't mean that we should, right? So that's why we try both options here. We say, what if AJ participated in the solution? Then the rest of the subsequence must have involved values that are bigger than AJ. So now we take advantage of that first index here and say, well, let's look for only those subsequences that start at values bigger than AJ. That's one possibility. And it's very crucial that you remember to add 1 here. Okay, if you forget this 1 plus at the beginning, then you're going to have a really stupid recurrence which does not give you any information. So whenever you're including something explicitly and moving on, you should remember to include either the cost or value or whatever it is of that action, right? And here we're just moving on without doing anything, so there's nothing that needs to be added to the solution. So again, feel free to take your time to absorb this recurrence, make sure that it makes sense. You can in fact formally prove the correctness of this recurrence. I won't be doing that here, I will leave that as an exercise. But when we come back and look at a different way of approaching this problem, there I will talk a little bit more about formally establishing the correctness of these kinds of recurrences. Okay. For now, I just want to talk about one more quick sanity check, which is to make sure that our recurrence does not go about in circles, does not have circular dependencies, and does not loop forever. So let's just draw out the DP table here. Remember, this is going to be a 2D array because we have 2 indices. So let's say that I is our row index and j is our column index. And so when we are trying to compute the DP entry at the ith row and the jth column, so I is the thresholding factor and j is where we are operating in the array, then let's think about what are the entries that we need the help of to be able to calculate this recurrence. So remember the 2 entries that we pinged were dp of I comma j plus 1. This was when we did not include the jth element in the solution for whatever reason. And the other one was j and j plus 1, right? So of interest is the j plus 1th column and the j plus 1th column at the ith row, as well as the j plus 1th row. So this is going to be a rough estimate of where the j plus 1th row is. Okay, so you're going to have to ping these 2 entries to figure out the value of the entry that you are currently at. Okay, and what you want to make sure therefore is that whenever you're trying to compute dp of ij, these 2 entries that you're relying on must have been pre-computed by that time, because if they're not, then you're in trouble, right? Because then you will go deep down a rabbit hole and not be able to get out of it. So just in this particular example, notice that we are quite safe, because when we started out with the base case, we computed everything in the last column, which was the singleton element. And remember, we said for each I, it's going to be either 0 or 1 depending on whether an is bigger than ai or not. So the last column is fully computed, and it's only after that that you will move on to computing the column entries for the n-1th column and so on. So you move backwards in this fashion starting from the end, and you will always be safe, because by the time you reach the jth column, all the columns that are in front of it would have already been computed. So while we are at it, let me also say here that the running time of this approach is order of n squared, because there are n squared entries here that need to be populated, and computing each of them only requires basically constant time. You need to look up these 2 entries and figure out if you should take a max or add 1, and these are all operations that are constant time arithmetic operations, so that's not too bad at all. It's going to be constant time per entry, but remember there are n squared entries, so the overall running time is order n squared. The overall space complexity also appears to be n squared, because it seems like we have to store this whole 2D array and it has n squared entries. However, notice that when you are computing the values of the jth column, you don't really need anything beyond the j plus 1th column. So you can actually throw away all of that information as you go along. So you start by computing the nth column, then you compute the n-1th column. When you go to the n-2th column, you can actually erase everything that you computed for the nth column, because that information is not relevant anymore. So if you're careful about optimizing a little bit, you can actually manage this in linear space. Even though the picture here may be a bit misleading, there is an implementation of it that involves just keeping 2 columns at a time, and that would be pretty safe. So that's our first approach to longest increasing subsequence. And let me just take this opportunity to build out a small checklist of things to be aware of when you're building up a solution like this. So the first thing you want to figure out is what to store. And this is like the semantics of your DP table. So to begin with, we said, we are going to store the value of the LIS for the subarray starting at the ith element and going till the end. That is an example of saying, okay, this is what we want to store. And when we enhanced that semantic, we ended up with this other definition where we said, let's store the length of the LIS of the subarray starting at the jth element, but now I only want to focus on those subsequences where the first element's value is bigger than a of I for some given index I, right? So all of that is this description of what it is that we want to keep track of, okay? And of course, whatever we decide to keep track of should be useful in getting us to the final answer. Otherwise, we have no motivation for storing whatever we decided to store. So we must have some way of pulling out the final answer from the pieces that we have identified that we said we will compute, right? So that's one thing to be quite sure about before you even get started. Speaking of getting started, typically you get started with a base case, which ensures that you can actually kick the recursion off and you don't have an endless pit in which you keep falling, right? So it's very important to work out the base cases, although the good news is that it's usually very easy to do. It's usually the easiest part of most DP-based solutions, but it's still very important, especially when you're doing implementation, to remember to do the base cases carefully to make sure all the corner cases have been worked out. So as a matter of making sure that your implementation doesn't get into infinite loops, that's very important. And the other thing is that sometimes you might encounter situations where you actually need a non-trivial base case. You might need something clever going on with the base cases. But most of the time, this is just something that's perfectly routine, easy to do, easy to forget. So that's why this is a reminder to always make sure that you're sorted on the base cases. Now, the heart of the DP is the recurrence relation. So this actually tells you how to make progress from the base case and upwards till you have computed everything that is of interest, right? And this is where you want to make sure that in your implementation, you're being careful about your recurrences. So notice here that we actually computed the recurrences over a table structure. If we had directly implemented this as a collection of recursive function calls, then you would be in trouble, because this will, as a recursion tree, this is just going to proliferate and have exponential complexity, and it'll go completely out of hand. So what we are doing here is a so-called bottom-up computation, where we are basically saying that, okay, let's work out the base cases first, and then essentially store information as we are going along, so that we can appeal to things that we have already stored instead of having to recompute them every time. If you just did a blind recursive implementation, along each of these recursive calls, you would be doing the entire computation again, and that would have been extremely expensive. Okay, so the fact that we're storing things as you go along is actually a crucial aspect of what we call dynamic programming. Some textbooks call this memoization, to basically indicate that you are committing to memory the intermediate values that are useful to you, right? So that's essentially the idea. In terms of implementation detail, there are usually two approaches. One is to say that, okay, you will initialize the whole table and you will populate it, from top to bottom, left to right, right to left, whatever makes sense, depending on where the base cases are. And the other approach is to say that, okay, you will write the recursive function as a recursive function, but you will have a small if statement which says that if we already know this value, then don't invoke the recursive call, just pull it out from memory. Okay, so this is just a matter of style in terms of how you implement it. The first approach usually involves writing a bunch of nested for loops or while loops or something like that. The second approach just looks like a normal recursive implementation, but with a bit of a case analysis thrown in to make sure that you are not doing repetitive computations again and again. So for some people, the second approach is nicer because it looks cleaner. The recursive relationship is very apparent, and it's just 1 or 2 lines of extra code to make sure that you are not doing all that extra computation. On the other hand, some people prefer the table-based approach because it feels a little more transparent, that you're kind of literally physically working out and navigating the whole recursive structure. And to some people, that's just clearer to see and visualize. So whether you do it through recursive memoization or whether you do it through the so-called table approach, like I said, the table approach is sometimes called bottom-up because you're building it up, and the recursive approach conversely is called top-down because you are starting at the big problem and you're then going down the recursive rabbit hole. Either of these approaches work perfectly well. For some problems, one seems like it's more natural than the other, but often it's just a matter of taste. Okay, so I'm not particularly obsessed with one over the other. Whatever suits you is perfectly fine. But the thing to avoid is to just have a pure recursive implementation where you're doing all of that extra computation. That would be quite disastrous, and that's the thing to avoid. Okay, so going further down our checklist, we want to make sure that our recurrence relation is acyclic, meaning that you're not looping forever. So we did this sanity check when we built up our recurrence for LIS. We said if we carefully go through the DP table, we'll never be in a situation where we are trying to ping a value that has not been computed. So that's an easy way of seeing that there are no circular dependencies. And this is something that's extremely important. You want to make sure there's no circularity in your recurrence, because otherwise, again, you'll keep going round and round, and that would not be a proper algorithm. Okay. Finally, for bonus points, you should be optimizing for time and space complexity. We did a little bit of that for the space complexity here, but it's like an algorithms person, you always end with the question, what's the time complexity and can we do better? And often you can improve on what you got on your first cut, and sometimes that's just really the best that you can hope for. But make sure that you do analyze your approach for the time complexity, the space complexity, and spend at least a little bit of time thinking about whether you can do better. And I should say that there's typically a lot of back and forth between these two steps. We saw one example of that between the previous discussion and the current one. So you come up with something you want to store, and then you start writing your recurrence and you realize that you're getting stuck, you're falling short. So that's probably because you're not storing enough information. So often you have to keep going back to the drawing board, figure out if you need to enrich your plan, your semantics, and then come back and try to work out your recursive relation again. So we're going to get a lot of practice with that sort of thing. Really, you may have seen DP before. So my focus here in these discussions is to perhaps help you think about how to think about DP, right? Because oftentimes we see solutions as given in the textbooks, and we're left wondering a little bit, how did people come up with that? So we might end up doing these little diversions where we come up with things that don't work and go back to the drawing board. And you might be wondering why we are doing that and why are we doing all these wrong approaches. And that's because I just want you to get a feel of what it's like when you are dealing with a problem out there in the wild where you don't have a textbook solution and you're thinking about it from scratch, you will often end up doing this sort of back and forth. So I'm just trying to simulate what that experience is going to be like. And we won't always necessarily start with a wrong answer, so don't always listen to me with suspicion. But I do want to emphasize that sometimes things look very clear-cut in textbooks or in lectures, but when people actually are coming up with their own solutions, it's not like a straight path like that all the time. There is usually a lot of back and forth before you can figure things out. I would definitely encourage you to go through as many practice problems as you can to get a sense of confidence for being able to sort of come up with your own recurrences for new problems. And we do have some exciting assignments lined up this week, so I hope you check them out. In the meantime, what we will be doing in the next video is looking at another approach to LIS, and after that we will move on to a couple of different problems. Thanks for staying with me, and see you next time.